Good afternoon. Thank you so much for making it on a Thursday afternoon. So I've been averaging around 15K steps a day, and that gentleman beat me to 30K. So I know you're all tired and probably thinking about your flight back home, but we do appreciate you coming over here for this session. So before I get started, can you please raise your hands if your AI infra costs have doubled this year? Wow, am I the only one? Okay, and my team is still not happy. So any guesses whether AI infra cost is going to go or double going into next year? Yes, no, maybe so? Yes. Any others? Yes. Thank you. All right, so just to introduce myself, I'm Anila Joshi. I lead strategic accounts for GenAI Innovation Center. And today I have with me our amazing partner from Autodesk, Kamal, and senior engineer from my team, who is the brains behind the solution, Mun. So we are going to talk about, let me change the slide. So we are going to talk about how Autodesk's actually accelerated their compute as well as the Bernini model, optimizing on the costs as well. So just to give you a brief background about Generative AI Innovation Center, we are a team of deep science, engineering, strategy, and architects, and we work very closely with our customers. And in fact, we embed our teams within our customers to not only identify the most impactful GenAI use cases, but also work with you to develop as well as deploy tailored solutions that can generate transformational value for your GenAI investment. So do reach out to us if you want to partner with us. So in this session, we'll start with the future of AI compute. So from our perspective, what does that look like? And we'll go through Autodesk's journey of AI, generative AI, and we'll specifically talk about the Bernini, which is the generative AI 3D model, and how Autodesk actually optimized the inference of the Bernini model. And we'll talk about why Neuron, and we'll also close out in terms of giving us our perspective of future of AWS AI accelerated chips. So these are some of the numbers. So according to Gartner, so this year, the spend for AI infrastructure is going to hit about $18 billion. And it is expected to double going into next year. Is this believable? Is this a number that you probably may have guessed? All right. So in terms of what we are hearing from our customers, flexibility has been the key. The bigger models and throwing more GPUs and infrastructure for bigger models is not always the answer. So at certain point, you would actually hit you will not gain any performance gains even if you add more parameters to the models. So the performance gains diminish after a certain point. And most of our customers are now looking at smaller fine-tuned models for their specific needs, and also flexibility to move between different models per se. So the infrastructure, in terms of the infrastructure flexibility of choosing the right resources for the right workloads has been one of the demanding asks from our customers. So we have been building our portfolio of the instances, the AI instances. It includes Gravitons, CPUs, GPUs, our own AWS AI accelerators, ASICs, as well as FPGAs. So these are many different ways. In fact, we released our Trainium 3 about 3 days back. So you have flexibility in terms of choosing many different instances based on your workloads and based on your needs. So with that, let me invite our partner and principal machine learning engineer from Autodesk to walk us through the AI model Bernini journey with us. Thank you.
Thank you, Anila. So our mission at Autodesk is to empower innovators to design and make anything, from building a new stadium, as you see here, to racetracks or VFX superheroes. In architecture, our models analyze environment factors like wind, noise, and flood risks, and generate optimized architecture layout and industrial designs. In construction, we automate tasks by extracting data from drawing and specification, handling things like bid forwarding and takeoff. For entertainment, we transform live-action footage into editable CG scenes and generate 3D motions using natural language instructions. In manufacturing, our models generate 3D models and design alternatives, allowing rapid exploration of concepts using simple prompts. To support the scale of our generative AI work, our compute demand has increased significantly. We have seen a need for about 200% increase in our deep learning compute in the last 2 years. This slide shows an example of our deep learning workflow. We start by identifying and ingesting data. For this example project, we ingested about 300 terabytes of data. During data processing, we deduplicate the data and convert it to formats that can be consumed by deep learning models. We run several model training experimentation using different model architectures and hyperparameters and evaluate their performance. Once the model performance is satisfactory, we deploy the models to be used in application. For this example project that I show here, we ran more than 300 experimentation, and we had 10 models deployed at the end. This is an overview of our training and inference infrastructure that is built on AWS EKS. We also use Ray for scalable distributed compute for model training and model deployment. And we have developer-friendly interfaces for model training. For inference, we use RayServe and GitOps model deployment with Argo CD. We also have observability built in using Prometheus and Grafana. We have been driving the 3D generative models research for years, with publication in top conferences such as CVPR and ICML, as shown by this timeline. We have been working with AWS to optimize one of our generative 3D models, Autodesk Bernini, to efficiently run on the AWS Neuron chips. Bernini is capable of generating 3D objects from various inputs, including images, point clouds, or natural language. This slide gives an overview of the pipeline we have built, which involves a diffusion model and various data representations like wavelet, TSDF, and to produce a final 3D object. So the process begins with context encoding of the input. This is followed by the reverse diffusion process, which generates a wavelet, a compressed wavelet representation of the 3D object. We then perform an inverse wavelet transform to get the TSDF, or truncated signed distance function, of the 3D object. And the final step is to convert the generated TSDF representation to mesh. Now I will hand the presentation over to our collaborator, Moon, to talk about AWS Neurons.
All right. Thank you, everyone. Thank you, Kamal. Thank you, Anila, as well. How many of you used Inferentia Neuron before? Yeah? Are you from NODA? Yeah, okay, hi. Good to see you again. Anyone else? Or who's managing their AI infrastructure, compute infrastructure? Can you just raise your hand? No? Are you guys all using just GPT or Bedrock models? Anyone run their own models? Well, I'm sure you guys have your own AI compute, or like I'm sure you guys use GPUs in your workflow sometime, right? So today I'm just gonna talk about what it means to work with Neuron. I'm just gonna take a step back and tell you about what Neuron is and why we need an AI accelerator in the first place. Give me 1 second. Why do we need an AI accelerator, right? Well, it's well known that there are a lot of matrix multiplications for deep learning, right? This can be up to quadrillion floating point operations for GPT, as an example, right? And many of your simple deep learning neural networks will also have maybe billions of matrix floating point operations, right? And in order to enable this kind of workload, we need to parallelize the operations. But CPU is not a powerful machine or device. It is powerful, sorry. It is powerful, and technically you can parallelize as well, but it's expensive, right? You can have a bunch of CPUs, but it's going to be very costly. You cannot have Zion or hundreds of Zions to run your deep learning models. And that's why we need a specialized machine accelerators that is specialized for matrix multiplications. And GPU can be one of them, but Neuron can be more purpose-driven. All right. Okay. So we all know what a matrix multiplication looks like, but I just want to highlight that there are a lot of elements in an input matrix that gets reused in computation. For example, this is 4x4 matrices, and each element here, if you look at the top left, A11, that gets reused up to 4 times, right? And you can imagine what the scale would look like if we had like 512 and 5 by 512 by 3, with a batch size of 32, and there will be a lot of repetitions. And this is important context for Neuron, which I'm going to explain in a bit. So one way of parallelizing would be using a machine that has many cores like GPU. But the challenge is that each core would be reading from a shared memory independently again and again over time. And this can create an overhead and extra power consumption. And so we can ask the question, can we reduce memory I/O, right? What if we can read data once and run it through multiple cores? And that's where systolic arrays come in. They use something called multiply and accumulate operation. I made an animation to show what it looks like, but essentially you load the data once, then arrange it so that the elements slide across the grid of processing units. And when 2 elements meet, they multiply and accumulate on the processing unit. Right? And because of that operation, we can make chips that are much cheaper and simpler. It requires less memory access and bandwidth needs. The hardware layout and data flow is simpler. And it also requires less transistors for scheduling and data flow. Therefore, you can save some transistors for that space. And that's why AWS AI chip can give you better cost efficiency. I believe it's about 20% cheaper per hour, but it often has better latency and throughput, so it can be actually up to 70 to 80% cheaper per inference than GPU. Here I'm only showing Inferentia 2, but Trainium also has a similar architecture, and these chips have multiple neuron cores with different types of engines, HBM, and other components that enable communication between cores and other devices. So here's how neuron core looks like and how data flows between engines and memory tiers. Tensor engine is essentially the main systolic array that I explained earlier for matrix-to-matrix multiplication. And vector engine is used for spatial operations that are often reducing functions. Scalar engines is used for accelerating element-wise operations that are often nonlinear. And GPSIMD, or general purpose SIMD engine, is essentially a mini GPU that can distribute a single instruction into multiple cores and data parts. And they are programmable using C. So if you think there are operators that are not fit for a systolic array, you can essentially write C code and run it directly on there. And this is how PyTorch code runs on Neuron. The code gets converted into A10 C++ implementation or intermediary representation. And this happens on Torch SDK. And then Neuron SDK takes over and compiles the graph, fuses operations whenever it can, schedules the engine to run on, and then arranges the data and waits to that systolic array format. Then it converts data into NEF, Neuron Executable File Format, and eventually all the way down to the instruction set so that it can run on the core. One thing I want to highlight in terms of developer experience is that they're now releasing something called Torch Neuron, which allows you to use Neuron on PyTorch more natively. Oh. Yeah, here we go. Yeah, so here you can see that with CUDA, you can, oh, it automatically goes back. With CUDA, you can use .2 CUDA, right? And same thing for Neuron. You can now use .2 Neuron to simply move your data and model onto Neuron devices. This wasn't the case. Just about a few months ago, we had to compile each model separately, and you have to load the compiled artifacts and then compute. But now with this SDK, it will make the experience a lot more seamless. So when is it a great fit for Neuron? I say that, and a lot of customers ask me this all the time, and I tell them, well, it's not a one-size-fits-all type of hardware, because just like CPU, you cannot run everything on there efficiently. And again, it's a purpose-built hardware specialized for matrix multiplication. So it performs really well on models like transformers or embedding models that are mainly prioritizing matrix multiplications. It's also really powerful for some workloads that often require sub 5 milliseconds latency, like intent classification on search bar, because it has a lot less overhead than, let's say, GPU, right? And it's also great for organizations that want to get the best bang for the buck. With less data reads, it often has higher arithmetic intensity, AI. So it might give you better utilization and higher throughput. And actually, this was the case for Bernini and some other models for Autodesk. All right. And another thing I want to mention quickly is that input and output size matters. Essentially, your production settings really matter. We did an experiment with Autodesk for other sets of models using variable inputs and output sizes, and also different batch sizes. And we found that with lower batch size, lower sequence length, Neuron was giving at least 2 times better performance, which would translate to at least 3 to 4 times better price performance, meaning performance per inference, latency per inference. And the yellow region that you see is actually the production setting that Autodesk uses for that particular model. And so this really makes the Neuron more favorable than other devices. So yeah, just understanding how your production setting looks like is really critical. And these are some of the metrics that we get from running their models on Neuron. We have 75% latency reduction, achieving up to 80% cost saving, and up to 4 times better throughput and performance in general. All right, so let me go back to Bernini, and let's see how Bernini fits on Neuron. So Kamal explained this is the model, and these are the pipelines. We have encoder, then the reverse diffusion, wavelet transformer, and then the triangularization for converting TSDF into 3D mesh. But we can break it down even further, and I have an algorithm version of that. And what's important to note here is that each component has its own torch model. And like the decoder, random tensor generator, UNet, and wavelet, and we want to break it down into components and compile them separately. We compiled it using Neuron Trace API, but like I said before, you can use the Torch Neuron SDK that's coming up actually next week, so then it will simplify your experience by a lot. And once you compile all the models, you can save those artifacts onto S3. And Kamal mentioned they use Rayserve, so you can essentially have Rayserve deploy the containers, and the containers can pull the artifacts as well as model weights onto the image at the runtime initialization, and have that deployed onto your fleet, AKS fleet. And we were able to get up to 28% cheaper per prediction. So this graph is showing the price per 1 million inferences for both inference X large and G5 X large. And this shows at for a different concurrency level, you get a better price performance. So essentially, it's performing. It's giving you a cheaper cost when it's resting as well as when it's super busy. Yeah, so we're just wrapping up here, but I just want to share some of the lessons we learned and some of the things that you can carry for your workloads. So again, it's not one size fits all, right? We try so many different devices and models, and some of them fits really well on GPU, some of them fits really well on Neuron, and even CPU. And then also the model architecture matters a lot. The flexibility is a key for long-term success, like Anila mentioned. And we believe that specialized hardware will continue to scale after, we are towards the end of Moore's law, essentially, right? It has plateaued, and so now we are trying to scale the compute efficiency, and specialization is the key. And lastly, I mentioned this earlier, but production setting is going to impact your latency by a lot. So understanding your batch size and expected sequence length and other factors will help you go a long way. All right. Thank you. And I think we can just use majority of the time for conversation. I'm happy to explain different things about Neuron, about Bernini and other things.